space dose into liquids. In a vacuum, a substance can be a solid or a gas, but liquid states don't exist. This means when a comet warms up, its ice sublimes rather than melts, turning directly to gas. Exceptions exist, however. When exposed to ultraviolet light, the mixture of ices found on comets and in planet-forming disks can bubble and flow like a liquid, even at very low temperatures. The discovery could help explain how giant planets form, and even how the conditions for life on Earth rose. The ice we see on comets or the moons of the outer planets is not made from pure frozen water. Instead, it represents a mixture, principally of water, methanol, and ammonia, but also including more complex molecules that form the building blocks of life. Dr. Shogo Tachibana of Hokkaido University replicated the simpler components in the lab and exposed layers just a few micrometers thick to ultraviolet light. At temperatures of 65th 150th Kelvin 208th to 123rd C 343rd to 190th F, the ice bubbled like a liquid. The same occurred when Tachibana tried the experiment with pure water ice, but at somewhat lower temperatures. On the other hand, Tachibana and co-authors report in Science Advances that ice with the same composition, but not exposed to UV radiation, did not respond the same way. The bubbles were a few hundredths of a millimeter, less than a millionth of an inch across. When temperatures were raised a little further, the ice sublimed, leaving behind organic materials and traces of bubbles. The bubbling was a result of the ice molecules being broken apart by the radiation, and molecular hydrogen released in the process escaping. Higher concentrations of water reduced the amount of bubbling, which suggests that most of the hydrogen was coming from the ammonia and methanol. Similarly, the liquid-like behavior has been attributed to the rearrangement of hydrogen bonds induced by the UV radiation. Crucially, the amount of UV light required to induce liquefaction is similar to that in parts of protoplanetary disks exposed to a sun-like star. In other words, something similar was probably occurring on the surface of planetesimals in the early days of the solar system as they began aggregating into planets. The authors calculate the same thing may occur on the outskirts of planet-forming disks in star clusters as a result of radiation from sibling stars. Although any hydrogen that bubbles off would reduce planetesimals' mass, liquefaction could make it easier for small objects to stick together, explaining how planets at the right distances from stars form so quickly. If the necessary components for life did indeed arrive on Earth from comets, understanding how these molecules respond in space could be particularly important.